Okay, so we're looking at the top of page 90 in our workbook. And in this illustration, we are going to develop a new convergence test that allows us to determine the convergence of a series by comparing it essentially to an improper integral, something that we talked about earlier in the course. So let's look at the situation that we have together. There are a few things going on here. We've got a series, we've got a function, and then we've got a relationship between the two. The formula for the series and the function are the same. That's the relationship. Okay, we're going to be drawing a couple of pictures just to get a feel for what this test is saying. I'm going to call the one on the left figure 1. And we're going to start by just drawing in some rectangles together. Okay, you might recognize these rectangles that I'm drawing as being left-sum rectangles from Calculus 1 because each rectangle hits the curve at the left-hand endpoint. Okay, and what we're going to be particularly interested in here are the areas of these rectangles. All right, so let me ask you first, what is the width of every rectangle that we just drew in? Okay, you can look at the picture and see that the width of each rectangle is 1. To get their areas, we need to figure out what the height is. Okay, so if we focus on the first rectangle that we drew, okay, the one right here, the height of it is right about there. And notice that it touches our curve at the left-hand endpoint of 1, which means that its height has to be f of 1, but from the formula that we were given, f of 1 is just equal to a1, the first term in our series. Okay, so if we put all that together, we have a rectangle whose height is a1 and whose width is 1. Its area then has to be a1, the first term in our series. Okay, and if you move on to the second rectangle now, okay, it touches the curve at 2, so its height is actually a2, which means that its area is a2 times 1, or a2. And this pattern continues. Every rectangle has an area that's equal to one of the terms in our series. Okay, so what we're going to do down below now is to do a little area comparison, all right? So the first thing I'm going to write is just the terms in the series itself. It goes on forever. And I'd like to compare that series sum with the improper integral from 1 to infinity of our function. Okay, and the question I'd like to ask you is, which of those two things is bigger? Okay, let's start with the integral, okay, that's over here on the right side of our equation. Remember, an integral is just the area under our curve. So asking you which of these two things is bigger is like asking, is the sum of the area of all the rectangles bigger, or is the area under our curve bigger? Okay, you can look at the picture and see that the rectangles stick out above the curve, so the rectangle areas must be bigger than the area under the curve. So our inequality must go in this direction. Okay, so we will kind of file that equation for later. I'm going to call it fact 1. It's just a comparison of areas. Okay, and now we're going to draw a similar picture over here to the right. Okay, this time we're going to draw our rectangles a little bit differently, though. This time we're going to draw them to be right sums. Okay, so every rectangle now touches the curve at the right-hand endpoint. We can ask the same question, what would the areas of those rectangles be? Okay, well this time, if you focus on the first rectangle, it touches the curve at x equals 2, this number, and so the height must be a2 this time, giving that first rectangle an area of a2. Okay, and if you keep doing that, the pattern's going to continue. So we're getting areas to be terms in our series. The only difference is that we're starting from a2. Okay, so if we do another area comparison this time, we just kind of write down the areas of our rectangles one at a time. We're starting with a2 and going on forever. And we could ask the question, how does that compare again with the integral from 1 to infinity of f of x. Okay, well this time the rectangles are below the curve. Okay, so the sum of the rectangle areas must be less than or equal to the integral. Okay, well, if you look at the second equation here, we're kind of missing the term a1, the first term in our series, and so we can do a little algebra to kind of recover that missing term. What I'm going to do is just add a1 to both sides of this equation. That's legal as long as we do it to both sides. Okay, and so that gives us just a rewritten version of this. On the left, by adding a1, we now have a1 plus a2 plus a3. In other words, all of the terms in our series. And over on the right, we've got a1 plus that integral. Okay, and it's still true that that's less than or equal. All right, so I'm going to call this fact 2. And we're going to use these two facts to come up with a convergence test that's called the integral test. Okay, so let's scroll down here. Okay, in the integral test, there are two parts to it. The setup is the same situation that we had above. We've got a function and a series, and then the relationship between the two is that the formulas are the same. Okay, here's what the first part of the integral test says. It says that if you have the improper integral of f of x, and you know that it diverges, then the series an also has to diverge. In other words, if the integral behaves in a way, the series has to behave in the same way. Okay, where does this statement come from? Okay, well, I claim that that actually comes from fact number 1 above. Okay, let me see if I can convince you of that. All right, so if you kind of take the first part of this statement, that the integral diverges, that's like going up to fact number 1 and looking at the right-hand side of that inequality and saying it diverges, which means that it must go off to infinity. All right, but if the right-hand side of this inequality is infinity, what is the left-hand side? It's telling us that the sum a1, a2, a3, and so on has got to be bigger than or equal to infinity. If we've got something that's bigger than infinity, it's got to also be infinity. In other words, the series diverges because it's bigger than the integral, which we know is infinity. Okay. And it turns out it goes the other way as well. Okay, so part 2 of the integral test says that if, on the other hand, the improper integral converges, then the series will also converge. Okay, and I claim that this statement we can kind of recover by thinking about fact number 2. Okay, so let's see if we can convince ourselves of this. In statement 2, we are assuming that the integral converges. Okay, so if you go back up here to fact number 2, if this integral converges, it means that it's a finite number, and so we're going to take that finite number and add it to a1. That's going to make this entire left-hand side finite. And so if you look at the left-hand side of the equation, that means that this sum of the terms in our series has to also be finite because it's less than or equal to a finite number. Okay, and so that's our justification that statement 2 down here is also a true statement. And there it is. That's our integral test. And basically, in a nutshell, what it's saying is that we can calculate an improper integral and use the convergence of the improper integral to tell what the series is doing. Okay, and we will do